Hello, fellow stats nerds, and welcome to Mrs. Pendry's podcast. This podcast supplements instruction provided in AP Statistics at East Davison High School. The textbook we use is The Practice of Statistics, 3rd edition by Yates, Moore, and Starnes. We are beginning our study of inference procedures with an introduction to confidence intervals. This podcast deals with topics from the first section of Chapter 10, Confidence Intervals, the basics. Thus far, in AP Statistics, we have analyzed data through numerical summaries and graphical representations, discussed methods of producing data including surveys, observational studies, and experiments, and calculated probabilities for a variety of random variables. Now it is time to turn our attention to methods of inference. Very often it is impossible to know information about an entire population, so we must take what we know about a small group from the population and use that to draw conclusions about the population from which they come. That is the process called statistical inference, where we do draw conclusions about a population from sample data. The first method we will discuss is the process of creating a confidence interval, which is designed to capture a certain population parameter in a certain percentage of all samples. Confidence intervals estimate the value of a population parameter. This gives a range of population values for which our sample is very likely. Because formal inference requires the long-run, regular behavior that probability describes, it is important for us to have reliable results. Therefore, when you use statistical inference, you are acting as if the data are a random sample or come from a randomized experiment. If this is not true, your conclusions may not be valid. Inference is the process of trying to say something about a population from information we can get from a sample. Sample values, which are our statistics, vary, but population values, which are our parameters, do not. This means that while there is one true population parameter, the results you get from different samples will differ somewhat from one sample to the next. We will now focus our attention on page 618, example 10.1. Those of you who may be joining us without the Yates, Moore, and Starnes 3rd edition of the Practice of Statistics may click on the link, which will take you to a copy of the information we will use. In this example, we will look at estimating an unknown parameter using a scenario involving IQ scores and admissions to a university. The admissions director at Big City University has a novel idea. He proposes using the IQ scores of current students as a marketing tool. The university agrees to provide him with enough money to administer IQ tests to 50 students. So the director gives the IQ test to a simple random sample of 50 of the university's 5,000 freshmen. The mean IQ score for the sample is 112. That is our sample mean, also called X bar. What can the director say about the mean score, which is mu, of the population of all 5,000 freshmen? Is the mean IQ score, mu, of all Big City University freshmen exactly 112? Probably not. But the law of large numbers tells us that the sample mean, which is X bar, from a large simple random sample will be close to the unknown population mean, which is mu. Because our sample mean in this problem is 112, we guess that the population mean is somewhere around 112 as well. How close to 112 is mu likely to be? To answer that question, we must also ask, how would the sample mean, X bar, vary if we took many samples of 50 freshmen from the same population? The concepts that follow were all introduced in our study of sampling distributions in Chapter 9. The mean of the sampling distribution of x bar is the same as the unknown mean, mu, for the entire population. The standard deviation of x bar for a simple random sample of 50 freshmen is found by the formula standard deviation of the population divided by the square root of the sample size, which in this case is the square root of 50. Sigma in this exact problem is the standard deviation of individual IQ scores among all big city university freshmen. Suppose that these IQ scores have a standard deviation of 15. Then the standard deviation of x bar is found by taking 15, dividing it by the square root of 50, and that is going to be approximately 2.1. The third concept deals with the central limit theorem. And in this problem, we know that the mean x bar of the 50 scores has a distribution that is close to normal. This is because, although we do not know that the population varies normally, we do know that n is equal to 50, which is a large enough sample that we can assume that the sampling distribution of x bar varies approximately normally. So those are all concepts that we did cover in Chapter 9, which are also very important to these next upcoming chapters as well. Now, we can use all of this information to create a confidence interval that will frequently capture the true population mean IQ score of all 5,000 freshmen based simply on our results from our simple random sample. The first step in this process is to estimate the unknown population mean mu. To do that, we're going to use the mean given in our problem of x bar from our simple random sample. The second thing to note is that although x bar is an unbiased estimate of mu, it will rarely be exactly equal to mu. So our estimate does have some error. We call that the margin of error. In repeated samples, the values of x bar approximately follow a normal distribution with a mean equal to mu and a standard deviation for x bar equal to the standard deviation divided by the square root of n, which in this problem is equal to 2.1. The fourth concept comes from Chapter 2. If you will recall, that is the chapter where you were first introduced to normal distributions. We discussed something called the empirical rule, also known as the 68, 95, 99.7 rule for normal distributions. The 95 part for that rule says that in about 95% of all samples, the mean IQ score, which is the x bar for that sample, will be within two standard deviations. In this problem, that's going to be 2.1 times 2. So therefore, we are within 4.2 values of the population mean, which is mu. Moving along to the next set of information. We can find that whenever x bar is within 4.2 points of mu, mu is also within 4.2 points of x bar. This is going to happen in about 95% of all samples. So based on what we know about the sample mean, the unknown population value will lie between x bar minus 4.2 and x bar plus 4.2 in about 95% of all samples. You can also say that the unknown value mu falls within x bar plus or minus 2 standard deviations from the mean. If we estimate that mu lies somewhere in the interval that is described above, you can see how we have taken our values for x bar, subtracted 4.2 in one case, and then added 4.2 in the other to obtain our interval, which will go from 107.8 to 116.2. In calculating the interval using this method, we would be calculating this interval such that it captures the true population IQ score of all of these incoming freshmen at Big City University in about 95% of all samples. The big idea in this problem is that the sampling distribution of X bar tells us how big the error is likely to be when we use X bar to estimate mu, because as we stated earlier, it is very rare for the mean of your sample to be exactly equal to the mean of your population. That is where the margin of error comes in, which helps us to create our confidence interval. Now, let's return to our PowerPoint to further investigate how confidence intervals behave. As we found in the previous example, a confidence interval is a set range of population values for which our found sample is likely. The confidence interval applet that we will be looking at momentarily will provide you with a visual of what it means for the interval to capture the true population mean. If you would, please click on the confidence interval applet and you can follow along with me as we investigate the various options available on this screen. Feel free to read the information at the top of the page. I will talk through a lot of that as we go on through this example. Let's look at the various options on this applet. First, in the middle of the screen is a drawing of a normal distribution, a normal curve, which represents the various values from some population. Notice that the population mean, mu, is marked with a green line, and the first through third standard deviation markings are provided on either side of the population mean. On the left-hand side of the screen, you can select the confidence level you wish to obtain. We will begin our investigation with the 95% confidence interval because that is generally the most common confidence level used. However, it would be wise for you to come back to this applet and further investigate the 80%, 90%, and 99% confidence levels. On the right-hand side of the screen, there are two buttons. The sample button is used to select a sample, one sample at a time. When this button is selected, it will calculate the sample mean, X bar, and will also calculate the interval of values, 2 standard deviations above and below the mean for our sample. Because you're going 2 standard deviations out, that is our 95% confidence level. As long as the line representing the interval crosses the mean line from our normal curve, our interval has captured the true population mean value. If it does not cross mu, the line will turn red, indicating that our interval failed to capture mu. So let's try this. If I click on the sample button, notice how my screen changes. Okay, I now have one line down below my normal curve. Notice that there is a small red mark in the middle of that line. That is where the sample mean for my sample will occur. Now, the line is created such that it is equidistant on the left-hand side of the mean and the right-hand side of the mean. And these values are not arbitrary. Because I am looking at a 95% confidence interval, the endpoints of that segment are found at 2 standard deviations below the mean and 2 standard deviations above the mean. Also notice that my sample mean and the population mean are not exactly equal. But because my line is a black line and it crosses over the line indicated by the population mean, our range of values has captured the true population parameter for this problem. Now, let's select another sample. Okay, this sample is not vastly different from the previous example. It too is black. It also crosses the green population mean line. And if you'll notice how these numbers have changed under the hit, total, and percent hit settings. I have got 2 total simple random samples, and I have hit the true population mean in both of those. Therefore, I have a percentage of hits at 100%. Now, I have a couple of options from here. I can either continue selecting additional samples one at a time, and notice that every single one of my samples up until this point has been black. It has captured my population mean. Thus far, I have collected 8 simple random samples. The last simple random sample that I chose is indicated on my graph with a red line. Please notice that that red line does not cross my green population line. Therefore, based on the values in that simple random sample, once I obtained the average and then calculated 2 standard deviations above and below that average, I failed to capture the true population value. So now I only have 7 hits out of 8, which gives me an 88% hit rate. Prior to my choosing the 8th simple random sample, my percent hit remained at 100%, meaning every simple random sample that I had collected up to that point captured the true population value. Based on my confidence level, I was only supposed to have 95% of them capture the true population value. Whenever I obtained the 8th random sample, that dropped my percentage down to 88%. So we went from 100% of the time capturing the true population value to now only having 88% of my samples truly capture the population mean. Now, we can continue selecting samples one at a time, or we can speed this process along and choose 50 all at once. So let's do that. Now, notice that as I selected my 50 random samples, I end up with 55 hits out of 58 total simple random samples, which gives me a 95% hit rate. Therefore, 95% of all of my samples captured the true population mean. Interesting, after only 58 trials, I have obtained the exact confidence level that I had indicated. We can continue selecting samples, and notice that as I select the next 50, my percentage changes slightly. Again, you can continue this process as long as you would like. Sometimes the percentage may go up slightly, sometimes it may drop down. Regardless, you are staying right around that 95% confidence level that we had set in the very beginning. At any time during your investigation, you may hit the reset button at the bottom of the screen and select a new set of simple random samples, either one at a time or 50 at a time, to see if this process of my percentage hit matching or coming close to matching my confidence level will hold true. And if you have a large number of repetitions, it should. Another option is after you hit reset, you may like to change your confidence level, and you can pay attention then to what that's going to do to the size of your interval, as well as how frequently you capture that true population mean. Feel free to take time to work with this statistical applet. Let's now return to the PowerPoint presentation to discuss additional terminology associated with confidence intervals. We've already talked about confidence intervals and confidence levels using our statistical applet. A confidence interval is calculated using a formula that in general takes some estimate, adds some margin of error, and subtracts some margin of error to it. Now, our estimate in the previous example was x bar. Our margin of error determines how far away from the mean we're willing to deviate. In the example on IQ and college admissions, as well as in the statistical applet, we had selected 2 standard deviations. The confidence level that we select gives the probability that the interval captures the true parameter value in repeated samples. Remember that from the applet we could set that interval, that confidence level, to be 80%, 90%, 95%, or 99%. These are 4 options that you have. The confidence level calculates the success rate for the interval. It is important to note that our confidence is in the procedure used to generate the interval. We are confident that an interval so constructed, as we described earlier, will contain the true population value a certain percentage of the time, and that percentage corresponds to our confidence level. Please pay attention to the interpretation of a confidence interval. We will now look at example 10.3 on page 621 of your text. Again, if you do not have a textbook, simply click on the link and you may follow along. In this example, we will continue our investigation of IQ and admissions, specifically focusing on interpreting a confidence interval. Our sample of 50 freshmen gave an x-bar value equal to 112. The resulting interval we obtained by taking our estimate 112 and then adding and subtracting 4.2, which was our 2 standard deviations away from the mean, set up by our 95% confidence level. One way that you can write that interval looks a lot like an ordered pair. But now in statistics, whenever we see an interval written, such as this, we know that we have a minimum as well as a maximum value. In our IQ score problem, we found that the interval ranged from 107.8 up to 116.2. We would say that we are 95% confident that the unknown mean IQ score for all big city university freshmen is between 107.8 and 116.2. Now remember, we do not know the true population mean IQ score. We are just trying to estimate what we have found. So you have to understand the basis for our confidence. There are only 2 possibilities. First of all, the interval between 107.8 and 116.2 does indeed contain the true population IQ score. Or second, our simple random sample was one of the few samples for which x bar is not within 4.2 points of the true IQ score. Only 5% of all samples give such inaccurate results. And if you will recall from our statistical applet exercise, if our simple random sample did not capture the true population mean, it turned red. We cannot know whether our sample is one of the 95% for which the interval x bar plus or minus 4.2 catches mu, or whether it is one of the unlikely 5%. The statement that we are 95% confident that the unknown mu lies between 107.8 and 116.2 is shorthand for saying we got these numbers by a method that gives correct results 95% of the time. The percentage is out of all 100% of samples that we may obtain. Be careful not to make this into a probability explanation. Let us now return to our PowerPoint, which offers yet another reminder that when you are interpreting a confidence interval, it is not to be phrased using the language of probability. As you work through problems involving inference, There are several conditions which must be satisfied before we can create a confidence interval, and you must show that you have checked these conditions for using a confidence interval. First of all, the data must come from a simple random sample from the population of interest. This information should be given in the problem. The second condition which must be checked is that the sampling distribution of x bar is approximately normal. Recall that in Chapter 9 we discussed assessing normality based on the central limit theorem. The third condition involves independence. Individual observations must be independent when you are sampling without replacement. The population size, which is our capital N, must be at least 10 times the sample size, which is our lowercase n. This is one of our rules of thumb used before calculating the standard deviation of x bar, so it should be very familiar to you, as these are all issues we have discussed in previous chapters. However, in working through a problem involving inference, you must indicate in the write-up of your problem that you have indeed checked them. So please do not leave that very important step out of your work. Okay, next we're going to take a look at something called a z-star value, and this is a new concept for you guys, as well as confidence levels. Let's go back to our discussion about the empirical rule. When using the empirical rule, we say that the 68, the 95, and the 99.7 give us the approximate percentage of values that fall 1, 2, or 3 standard deviations respectively from the mean. In actuality, the standardized values, which are positive and negative z, that capture 95% of all values corresponds to a z-value of plus or minus 1.96, not literally 2. So while we say that for a 95% confidence interval, that tells us the percentage of the values that fall 2 standard deviations from the mean, that too is an approximation. The exact distance that 95% confidence intervals fall from the mean goes to negative 1.96 and positive 1.96. So we would say that for a 95% confidence interval, the z-star value is positive 1.96. Notice that we take only the positive value of z. Therefore, we call it z-star. Now, z-star is defined as the upper p critical value of the standard normal distribution. And that sounds really strange and really formal. But remember the explanation that I just gave you about the 68, 95, 99.7 empirical rule. 95% of all values fall between the z value of negative 1.96 up to positive 1.96. That positive 1.96 is my z-star value. And that z-star value directly corresponds to a confidence interval. If I change my confidence interval from 95 to 90%, I do not capture as many values. My confidence interval shrinks, therefore my z-star value gets smaller. If I extend my confidence level to a 99% confidence level, then my interval will be larger than what I had with a 95% confidence level. That corresponds to a larger z-star value. So smaller confidence levels have smaller z-star values, and the opposite is also true. Larger confidence levels have larger z-star values. These z-star values may be found on the back inside cover of your book or in your formula packet, your student resources packet, at the bottom of Table C. We will look more at working with the z-star values and with Table C in future lessons. So for right now, let's go ahead to the next slide, in which we are going to discuss the form of the confidence interval. While we will look at computing these confidence intervals in subsequent lessons, we're now going to investigate the pieces that make up a confidence interval and the process that you will follow when it does come time to complete a problem pertaining to these confidence intervals. We've already talked about the confidence interval in these terms. It may be found by taking the estimate plus or minus the margin of error. Now, if we take that into notation, which we have not seen before, our estimate is x bar, just as we had discussed in the IQ and admissions problem. We also see the formula for standard deviation for our sample distribution. That is the sigma divided by the square root of n. However, now, instead of us simply looking at some arbitrary number, such as 95% is 2 standard deviations, we're going to have a formula that works for any confidence interval, in which case we're going to take z star, and that's what you're going to multiply by your standard deviation divided by the square root of n. X bar is the estimate, plus or minus. Now here is a new term. Z star is called a critical value. Now we can have a critical value of a z variable, which you are accustomed to, or something called a t variable, which we will encounter in future chapters. The place where you see the standard deviation formula, sigma divided by the square root of n, that is called the standard error. So again, this is some new vocabulary for this chapter. Now, to construct a confidence interval, I have outlined the 4-step process that you must follow in every problem pertaining to confidence intervals that you calculate. The first thing you must do deals with your population parameter. You have to identify the population of interest in your problem as well as the parameter that you want to draw conclusions about. In our IQ example, our parameter was the IQ score for our population, which was all freshmen at Big City University. The second step in constructing a confidence interval requires you to check certain conditions. This is where we must check to see that we have a simple random sample. We need to have a normal sample distribution, as well as independence amongst our observations. We have discussed these issues on a previous slide, so please refer back to that slide for the processes that you go through to check each of these conditions. The third step in constructing a confidence interval involves you actually calculating something. If the conditions that we checked in step 2 are met, you may carry out the inference procedure. In this chapter, that means we are going to take the estimate plus or minus the margin of error. We will add in the calculation portion of this process in our next lesson. Fourth, the last step, very important, do not leave it out, is interpretation. You must interpret your results in the context of the problem. There are 3 C's that you need to always include in your explanations. You must explain what conclusion you have reached. You must make a connection between your conclusion and the various concepts listed in the problem, and you must always include your conclusion in the same vocabulary that makes it a contextual response. Be sure always to interpret your confidence intervals correctly and do not phrase it as a probability interpretation. Okay, this slide includes a few main ideas that focus on the process that you can control in your confidence interval calculations. While there are many things that you have no control over, you can decide on a sample size, and you get to choose the confidence level that you are willing to have to obtain your results. So, let's suppose that you choose some value n. For every n value that you choose, you also are allowed to pick your own confidence level. Larger confidence levels correspond to higher confidence in your procedure, and that implies that you have a wider confidence interval. Recall that the interval is made up of 4 things: the estimate, x bar, the critical value, z star, the population standard deviation, which is sigma, and the sample size, n. You do not have any control over the population standard deviation. The x-bar value reacts to your sample size, and z-star is determined by the confidence level that you choose. So the more certain you want to be that you've captured the parameter, the more population values you must capture. So you've got to have a wider interval, a larger confidence level, which corresponds to a higher z-star value. Keep in mind the margin of error is obtained by the z-star times the population standard deviation divided by the square root of n. A small margin of error implies low confidence, and vice versa. A large margin of error implies large confidence. By manipulating your sample size, you can control the margin of error. From the formula, since you are dividing by the square root of n, a larger sample size will decrease the margin of error. Now, in all of this, remember that the population size is irrelevant when determining the margin of error. As long as the independence clause holds true, you must have a population that is much larger than the sample. All right, here's an example to show you how irrelevant population size is. Let's say we need a blood sample. A few cubic centimeters of blood are sufficient to do a complete blood analysis. Okay, so that's our sample, the number of cc's of blood. Well, whether that sample comes from an 89-pound 14-year-old female gymnast or from a 375-pound sumo wrestler, our population of blood is completely irrelevant. What we're worried about is having the same sample size. Now, for those of you in my class, you may remember that we had another example where we discussed population size versus sample size, and which of those had an effect. It all involved corn. It doesn't matter whether that scoop is going into a bag of corn or a truckload of corn. If it's the same size scoop, your margin of error will be the same in either case. Okay, let's now move on to a few warnings about constructing confidence intervals. First, what are the conditions that you had to check? The data must be from a simple random sample of the population, or at least a random sample. Different methods are needed for different designs. Now, we're going to focus on confidence intervals that capture a population parameter from a simple random sample. We're not going to use multi-stage sampling, cluster sampling, or stratified random samples, as those require more complex designs and inference procedures. The third caution: there is no correct method for inference for data that are haphazardly collected with a bias of unknown size. Fancy formulas cannot rescue badly produced data. The fourth thing that you need to be aware of that we have not discussed yet involves outliers. Outliers can distort your results because your whole confidence interval is based on the mean, and the mean is not resistant to outliers. So you need to decide what to do with any outlying value that you have. Select a larger sample, or just ignore that one value. The fifth thing that you need to pay attention to is the shape of the population distribution. Remember the central limit theorem. If the parent population is normal, the sampling distribution is automatically normal. However, with non-normality in that parent population, we run into the biggest problems when we have a small n value. With a small sample size, you simply do not have enough values from the population to create a sampling distribution that varies normally. The sixth thing that you need to pay attention to is the standard deviation sigma of the population. Our formulas will only work if we know that value. In reality, that doesn't even make sense, because if you knew the population standard deviation, you're going to have enough information to find the population mean. so you wouldn't have to estimate it based on a sample. But we have to have a starting point somewhere for our study of inference. And for those of you who understand that the processes described in this scenario are unrealistic and you need something more real-world applicable, well, the next chapters coming up are for you because they will not give you the population standard deviation, and you'll have some new formulas that you get to use to calculate your confidence intervals without that important piece of information. Once a confidence interval has been constructed for a population value, the language that is used to interpret the interval in the context of the problem is very important. My class always loves having that fill-in-the-blank statement that they can kind of go in and plug in their values to. So here it is for our confidence intervals. We are, and you can insert your confidence level. Say we use 95% confident that the true mean, and then you can insert whatever you were studying in the problem. So from our previous example, the true mean IQ score of, this is where you can pull in the population under discussion. So that would be the true mean IQ score of all big city university freshmen is between blank and blank. And that is where you can fill in your minimum confidence interval value and your maximum confidence interval value. That confidence statement means that these numbers were calculated by a method that gives correct results in 95% of all possible samples. The probability calculations of standard statistical inference describe how often the method gives correct answers. And there is a very fine line between how you discuss and how you interpret your confidence intervals. So do please be careful. Thank you for viewing this podcast. I hope it helps you as you begin your study of the inference procedure of calculating a confidence interval. If you should need to contact me, my email is kpendry@davidson.k12.nc.us. Again, that is kpendry, KPENDRY, at Davidson, DAVIDSON .k12.nc.us. Thank you again, and this is Kim Pendry, AP Statistics teacher at East Davidson High School.